Radius, is a AAA protocol mainly used to provide network access services. Due to its flexibility, it has been adopted in other scenarios as well. The authentication and authorization parts are specified in RFC 2865, while the accounting part is specified in RFC 2866. Radius is a client-server protocol. In the context of Radius, the client is the access server, which is the entity to which a user sends the access request. The server is usually a machine running Radius services that provides authentication and authorization responses containing all the information used by the access server to provide service to the user. The Radius server can act as a proxy for other Radius servers or other authentication systems. Also, Radius can support several types of authentication mechanisms such as PPP, PAP, CHAP, and EAP. It also allows protocol extension via the attribute field. For example, vendors can use the attribute vendor-specific type 26 to pass vendor-specific information. In the figure, we show a typical deployment of a Radius server, a Radius client, which is a wireless router in this example, and a laptop, which is a wireless client or wireless supplicant. Radius operates in most cases over UDP protocol port 1812 for authentication and authorization, and port 1813 for accounting, which are the officially assigned ports for this service. In earlier implementations, Radius operated over UDP port 1645 for authentication and authorization, and port 1646 for accounting. The authentication and authorization phase consists of two messages. First, the access server sends an access request to the Radius server that includes the user identity, the password, and other information about the requester of the access, for example, the IP address. Next, the Radius server may reply with three different messages. Access accept if the user is authenticated. This message will also include in the attribute field authorization information and specific vendor information used by the access server to provide services. Access reject if access for the user is rejected. Access challenge. If additional information is needed, Radius servers need to send an additional challenge to the access server before authenticating the user. The access challenge will be followed by a new access request message. Our figure here demonstrates the Radius exchange for authentication and authorization. The accounting exchange consists of two messages, accounting request and accounting response. Accounting can be used, for example, to specify how long a user has been connected to the network, the start and stop of a session. The Radius exchange is authenticated by a shared secret key between the access server and the Radius server. Only the user password information in the access request is encrypted. The rest of the packets are sent in plain text. Access Controller Access Control System Plus, or TACACS Plus, is a proprietary protocol developed by Cisco. It also uses a client-server model where the TACACS Plus client is the access server and the TACACS Plus server is the machine providing TACACS Plus services. That is, authentication, authorization, and accounting. Similar to Radius, TACACS Plus also supports protocol extension by allowing vendor-specific attributes and several types of authentication protocols. TACACS Plus uses TCP as the transport protocol, and the TACACS Plus server listens on port 49. Using TCP ensures a more reliable connection and fault tolerance. TACACS Plus has the authentication, authorization, and accounting process as three separate steps. This allows the use of different protocols, for example, Radius, for the authentication or accounting. Additionally, the authorization and accounting capabilities are more granular than in Radius. For example, allowing specific authorization of commands. This makes TACACS Plus the preferred protocol for authorization services for remote device administration. The TACACS Plus exchange requires several packets. First, start, reply, and continue packets are used during the authentication process. Next, request and response packets are used during the authorization and accounting process. Here is an example of an authentication exchange. First, the access server sends a start authentication request. Second, the TACACS Plus server sends a reply to acknowledge the message and asks the access server to provide a username. Third, the access server sends a continue with the username. Fourth, the TACACS Plus server sends a reply to acknowledge the message and ask for the password. Fifth, the access server sends a continue with the password. And sixth, the TACACS server sends a reply with authentication response, pass or fail. The figure you see here demonstrates the TACACS Plus authentication, authorization, and accounting exchange. Subject must be authorized. Authorization is the process of assigning authenticated subjects permission to carry out a specific operation. The authorization model defines how access rights and permissions are granted. The three primary authorization models are object capability, security labels, and ACLs. Object capability is used programmatically and is based on a combination of unforgeable reference and an operational message. Security labels are mandatory access controls embedded in object and subject properties. Examples of security labels based on its classification are confidential, secret, and top secret. Access control lists, or ACLs, are used to determine access based on some combination of specific criteria such as a user ID, group membership, classification, location, address, and date. Additionally, when granting access, the authorization process would check the permissions associated with the subject or object pair so that the correct access right is provided. The object owner and management usually decide or give input on the permission and authorization policy that governs the authorization process. The authorization policy and rule should take various attributes into consideration, such as the identity of the subject, the location from where the subject is requesting access, the subject's role within the organization, and so on. Access control models, which are described in more detail later in this lesson, provide the framework for authorization policy implementation. An authorization policy should implement two concepts: implicit deny. If no rule is specified for the transaction of the subject object, the authorization policy should deny the transaction. And need to know, where a subject should be granted access to an object only if the access is needed to carry out the job of the subject. You learned about the least privilege principle and need to know concepts earlier in this lesson. Access controls are defined by policy and cannot be modified by the information owner. MACs are primarily used in secure military and government systems that require a high degree of confidentiality. In a MAC environment, objects are assigned a security label that indicates the classification and category of the resource. Subjects are assigned a security label that indicates a clearance level and assigned categories based on need to know. The operating system compares the object's security label with the subject's security label. The subject's clearance must be equal to or greater than the object's classification. The category must match. For example, for a user to access a document classified as secret and categorized as flight plans, the user must have either secret or top secret clearance and have been tagged to the flight plan category. Discretionary access controls, or DACs, are defined by the owner of the object. DACs are used in commercial operating systems. The object owner builds an ACL that allows or denies access to the object based on the user's unique identity. The ACL can reference a user ID or a group or groups that the user is a member of. Permissions can be cumulative. For example, John belongs to the accounting group. The accounting group is assigned read permissions to the income tax folder and the files in the folder. John's user account is assigned write permissions to the income tax folder and the files in the folder. Because DAC permissions are cumulative, John can access, read, and write to the files in the tax folder. Role-based access controls, or RBACs, also called non-discretionary controls, are access permissions based on a specific role or function. Administrators grant access rights and permissions to roles. Users are then associated with a single role. There is no provision for assigning rights to a user or group account. We can see this in the following example. The user Derek is associated with the role of engineer and inherits all the permissions associated to the engineer's role. Derek cannot be assigned any additional permissions. Hannah is associated with the role of sales and inherits all the permissions assigned to the sales role and cannot access engineering resources. Users can belong to multiple groups. RBAC enables you to control what users can do at both broad and granular levels. In a role-based access controls environment, access is based on criteria that are independent of the user or group account. The rules are determined by the resource owner. Commonly used criteria include source or destination address, geographic location, and time of day. For example, the ACL on an application requires that it be accessed from a specific workstation. Role-based access controls can be combined with DACs and RBACs. Attribute-based access control, or ABAC, is a logical access control model that controls access to objects by evaluating rules against the attributes of entities, both subject and object, operations, and the environment relevant to a request. The characteristics of ABAC are the following. ABAC supports a complex Boolean rule set that can evaluate many different attributes. The policies that can be implemented in an ABAC model are limited only to the degree imposed by the computational language and the richness of the available attributes. An example of an access control framework that is consistent with ABAC is the Extensible Access Control Markup Language, XACML. The process of auditing and monitoring what a user does once a specific resource is accessed. This process is sometimes overlooked. However, as a security professional, it is important to be aware of accounting and to advocate that it be implemented because of the great help it provides during detection and investigation of cybersecurity breaches. When accounting is implemented, an audit trail log is created and stored that details when the user has accessed the resource, what the user did with that resource, and when the user stopped using the resource. Given the potential sensitive information included in the auditing logs, special care should be taken to protect them from unauthorized access. In Radius, the accounting exchange consists of two messages, accounting-request and accounting-response. Accounting can be used, for example, to specify how long a user has been connected to the network, the start and stop of a session. The Radius exchange is authenticated by using a shared secret key between the access server and the Radius server. Only the user password information in the access request is encrypted. The rest of the packets are sent in plain text. You can configure periodic Radius accounting packets to allow the Radius server, such as Cisco ISE, to track which sessions are still active on the network. In the following example, periodic updates are configured to be sent whenever there is new information, as well as a periodic update once every 24 hours. We have two separate applications. Application 1 and Application 2. Both applications require user authentication, as demonstrated in the following example. In the figure, the user Derek first tries to connect to an Application 1. Second, Application 1 prompts Derek for authentication. Third, Derek authenticates to Application 1. Fourth, Derek wants to connect to Application 2. Fifth, Derek is then prompted to authenticate to Application 2. And sixth, Derek is authenticated to Application 2. As you can see, this is not very user-friendly. In most environments, you are accessing dozens of applications throughout an enterprise network, or even applications hosted in the cloud. This is why Single Sign-On, or SSO, was created. This figure shows an example of a typical SSO implementation. Even though the steps in this figure are more elaborate than those in the previous figure, the user experience is better. This is because the user, Derek, only needs to authenticate once to Application 1, and then he can browse or access any other application that is a participant in the SSO implementation and that Derek is authorized to access. The concept of a centralized identity or linked identity is also referred to as federated identity. Federated identity systems handle authentication, authorization, user attributes exchange, and manage user management. The attributes exchange concept orchestrates data shared across different user management systems. The following attributes, like real name, may be present in multiple systems or applications. Federated identity systems counteract data duplication problems by linking the related attributes within all the elements that are participants of the SSO environment. SAML is used in SSO implementations. However, there are other identity technologies used in SSO implementations, such as OpenID Connect, Microsoft Account, formerly known as Passport, Facebook Connect, and others. SAML is an open standard for exchanging authentication and authorization data between identity providers. The following are several elements that are part of an SSO and federated identity implementation. Delegation. SSO implementations use delegation to call external APIs to authenticate and authorize users. Delegation is used to contain apps and services from having to store passwords and user information on site. Domain. A domain in an SSO environment is the network where all resources and users are linked to a centralized database. This is where all authentication and authorization occurs. Factor. You already learned about multi-factor authentication. A factor in authentication is a vector through which identity can be confirmed. Federated identity management is a collection of shared protocols that allows user identities to be managed across organizations. Federation provider is an identity provider that offers single sign-on consistency in authorization practices, user management, and attributes exchange practices between identity providers and relying parties. A forest is a collection of domains managed by a centralized system. Identity provider, or IDP, is an application, website, or service responsible for coordinating identities between users and clients. IDPs can provide a user with identifying information and provide that information to services when the user requests access. Kerberos is a ticket-based protocol for authentication built on symmetric key encryption. Multi-tenancy is a term in computing architecture referring to the serving of many users or tenants from a single instance of an application. Software as a service, or SaaS, offerings are examples of multi-tenancy. They exist as a single instance, but have dedicated shares served to many companies and teams. OAuth is an open standard for authorization used by many APIs and modern applications. OpenID, or OpenID Connect, is another open standard for authentication. OpenID Connect allows third-party services to authenticate users without clients needing to collect, store, and subsequently become liable for a user's login information. Passwordless is a type of authentication based on tokens. Passwordless authentication challenges are typically received and sent through SMS, email, or biometric sensors. Social Identity Provider, or Social IDP, is a type of identity providers originating in social services like Google, Facebook, and Twitter. With web identity, they are identifying data typically obtained from an HTTP request. Often these are retrieved from an authenticated email address. Windows identity is how Active Directory and Microsoft Windows environments organizes user information. And WS Federation is a common infrastructure federated standard for identity used by web servers and browsers on Windows Identity Foundation. Windows Identity Foundation is a framework created by Microsoft for building identity-aware applications.